everybody. Welcome. Nice to see you, Mitchell. How's it going? Hello, everyone. Great. So today the plan is to continue on with some of the material in chapter 2 that you guys did some reading, watching about quantifiers, negating quantifiers, and then we're going to start writing some proofs today. So we're going to wrap up worksheet 3 or start and finish it, pretty short worksheet, and then we'll just get our feet wet a little bit in worksheet 4, which is dealing with proofs, and then that's what we'll spend Monday working on. So before we get started, any questions? Just one reminder is that the homework is due, first homework is due tomorrow evening, late evening by midnight. So don't forget about that. Okay, so if there aren't any other questions, then let's just start by reviewing the stuff that was on the quiz. So looking at the results of the quiz, it seems like that went pretty well. But let's just make sure. Right, we've got these symbols. We use this kind of upside down A for all. We use this backwards E for there exists, and this means inside of a set. We haven't really gotten to this yet too much. So let me just say that it's nice to have this notation and write things concisely, but when you're writing proofs, the more sentences you use and the less symbols you use like this, the easier it's going to be to follow. So I think that once you see this notation, please don't rush into and eliminate writing words and just use symbols. That's kind of difficult to read sometimes. So there's kind of a fine line between how much you need to write out, how much you can write out symbolically. But we'll work on that. So for example, in A, we could translate this as Everyone Loves Raymond. Anyone familiar with that show? It's been like ages now. We need to update that. So this would be, for all over here is just more simply said everyone, and then for all X, they love Raymond. So certainly, right, if we compare these two statements, this would be something that would be much easier to read, more elegant actually than writing it like this. So just putting symbols there doesn't make the reader think, this person must know what they're talking about. So don't take these symbols as conveying that point. And then for the next one, right, this one we could read as, and I'll just kind of break it down by its components, right? This would be for all real numbers, that's the red part. There exists a real number y such that y cubed is equal to x. Any questions about that? And I guess one thing that we haven't been thinking about is, are these statements true or false? So these are all statements. What do you guys think? Does everybody love Raymond? No, I'm not. Personally, I'm not a fan of Raymond. Just kidding. He's fine, but probably not everybody does love Raymond. So this is probably a false statement. Is it true that for every real number x, there is a real number y such that y cubed is equal to x? So for example, let me pick an x that's like -7. Does there exist a y such that y cubed is -7? What do you guys think? There is, right? We can just take the cube root of both sides. Like that. So certainly we would fall into problems if we said y squared, but not for the cube. So this is a true statement. Okay, and then this one we could read as this is a there exists statement. So this would tell us that there is a real number y with the property y cubed is equal to x for all real numbers x. So let me just say, like, you could start this process by translating it bit by bit, like we did above over here. We could say there exists a y such that for all x in the real numbers, y cubed is equal to x. But then you can start to kind of polish that off and write it a little bit more clearly as you would explain it to somebody. So I don't want you to just start by translating things and just stopping there, but actually reading the translation and make sure that it just reads well. And if you can clean up the English at all, then that's great. Any questions? I see that there was a chat about, is the next homework due on Monday? The next homework is going to be due on Thursday still. So we're going to keep on that plan for the first couple of weeks. So the next homework will be due a week from tomorrow, and it's going to be on the stuff that we talk about today and the stuff that we talk about on Monday. Okay, so here's the translation for this. And again, these were kind of in the video, so I'll kind of leave it there. But if you do have questions, this is the time. You can't ask a video question, but you can ask me a question to let me know. So let me just say that when we talk about natural numbers, which we denote with this n symbol over here, natural numbers, these are positive integers. So they're like starting from 1. So these came from like, what are the most natural things for people to think about? 1, 2, 3, 4, 5. And 0 was actually not the most natural thing for people to think about at first. So this is saying for every natural number, x is either equal to 2 or it is composite. What do you guys think about this? So a composite number would be something like 4, which can be written as 2 times 2. So let me ask you, for something like 3, is this a composite number? So a composite is like the opposite of being prime, in other words. So the only way that we could write 3 as a product would be 3 times 1, right? So 3 is actually not a composite number, and it's not equal to 2. So that would tell us that this is actually a false statement. So 1, for example, is a natural number also that doesn't fall into that category. So there are other natural numbers that are prime, and that would be the counterexample for these. And so the questions that we need to think about as this semester goes on, well, first, we want to be able to read these statements. And then secondly, we need to think about how could we prove these statements? How can I prove something is false? How can I show that something is true? And so here we can see an example that we could prove this is false by giving a counterexample. Like x equals 3, that's a natural number. It's not equal to 2, and it's not composite. Okay, and then we can also practice going in the other direction. And so here's a statement: if x is a positive real number, then x over 2 is a positive real number. True statement. And so we've seen that this is a conditional statement. And so you might be thinking, how could we write this with a quantifier? I don't see a for all or there exists in this statement. When we're thinking about conditional statements, although it might not be explicitly stated, we should be reading these as for all statements. So it's really saying not just for certain values of x, but for any value of x, which is a positive real number, then this has to follow. So what this would be saying here is that for every real number x, if it is bigger than 0, that's going to apply that x over 2 has to be bigger than 0. Okay, again, for every differentiable function, for all functions that f is differentiable, this is going to imply that f is continuous. So one kind of point to make in these two statements is that we see conditional statements okay, we should read these as for all statements. And vice versa. If I have a for all statement over here, like for every, we can rewrite this as a conditional statement. And that's going to be really, really useful to do because that's what we do in this class is we prove conditional statements for the most part. And over here, we have a there does not exist statement over here. And so we can rewrite this there does not exist a statement equivalently as a for all statement. So there's kind of a subtle thing going on here with relating the negation of a statement that we'll clarify in a second. Questions at this point? Okay, so don't get enamored with all of this notation, please. I like words better than this notation, but just be aware that it's useful to be able to read these and translate between words and notation. Okay, so let me just open up a poll. Sorry, try not to read beyond this. I'd just like you to think about the following question. So here's a statement. If x is an even integer, right, then x is a multiple of 6. So this is a conditional statement here. I just like you to think off the top of your head whether or not you think this is, whether or not this is a statement and take another 10 seconds, please. Just a kind of knee-jerk reaction to this question. Okay, thank you for the responses. So there was a lot of confidence in 7 people that said yes, definitely. We had one person that was saying definitely not, and then we had a couple people that were on the fence. So it seems like people were leaning more towards yes as opposed to not. And so let me just kind of say that there are different ways that you might read this sentence. So if you said no, you might be thinking about the logic in this first bullet over here. And that is there are even integers that are not multiples of 6, right? So some of them are not. Since it depends on x, right, this makes it an open sentence. And on the other hand, people might think about this using like a truth table that we had last time, where this is P, this is Q. And so, you know, you can kind of just say, okay, X is an even integer. The conclusion is not always true. So that makes this statement false. And we don't like this ambiguity in math. There shouldn't be, I'm reading this and I think it's true. That's correct. I'm reading this and I think it's false. That's correct, right? There has to, there's a there is no gray area when we're doing logic. Statements are either true or they are false. So just be aware that when we're reading conditional statements, this is really reading this as for all integers x. And so for all integers x, right, there are some even integers like 2 and 4 that are not multiples of 6. So when we're kind of proving things in mathematics, we're usually going to be proving things like this. Is it true that P implies Q? And so since for all statements are actually implications and vice versa, we're going to have a nice set plan for how we can prove things like this. We'll have some various proof techniques. So it's going to be useful for us to take a for all statement, like some of these in 3, and rewrite them using implications, meaning as a conditional statement. So for example, this one over here, I haven't done anything. I haven't finished this, right? I'm just first going to take that symbolic sentence and just rewrite it in terms of words. Okay, but this is still a for all statement, so I haven't rewritten this in terms as an implication yet. Does anyone see how we can write this as a conditional statement? Okay, meaning if and then. Mike is yours if you want to try it, or the chat room. What do you think the hypothesis here is?
Couldn't we say if given real number x, then there exists a real number y such that y to the third equals x?
If x is a real number, sorry, what was the second part, Giselle?
If x is a real number, then there must exist real number y such that y to the third is equal to x.
Yeah, I think that captures that statement, just rewriting it as a conditional. Yeah, thank you, Giselle. Okay, and then we'll have some techniques to say like, okay, I can start with, I'm going to assume the hypothesis is true, and then how can I use some logic to therefore get that the conclusion must follow. Okay, so maybe over here, if I were to just kind of read this in words, part B, oh, good, great. Here come all these suggestions. Thank you, everyone, for getting these in. Yeah, and you're welcome to chat them in to everyone. You're welcome to chat them in to me with whatever you prefer. Yeah, and so now in part B, we have like for every natural number, I'm just going to read it as opposed to write this out in English, right? So this is saying for every natural number x, if x is even, then x is equal to 2, right? Or x is composite. And this was kind of one of the statements that we had on the previous page. And so this is already kind of written out as a conditional, right? So this little symbol here means then. So here we could say if x is even, and it's a natural number, so that's how we can rewrite that as a conditional statement. And again, I'm going far out of my way not to use any symbols here. And I think somewhere in between what I'm doing and what the original statement is probably a good place to be. Anyone want to take a shot at the last one to write this as a conditional?
Oh, can I go?
Yeah, sure.
If a function is if the function is differentiable, then the function is also continuous. Or you can say like if function f is differentiable, then function f is also continuous.
Yep. And yeah, I think, thank you, that maybe a good qualifier here is to add something that says the function. That's right. So I would say that when we're introducing a new letter or new variable like f, it helps to tell the reader what f is representing. That's right.
Would that also be correct if in the second part you took out the f and you just had then it is continuous, or should you always specify that you're referring to f the function?
I think the more specific that you are, the less interpretation you leave for the reader, the better it's going to be.
Okay.
So something like that is, so the question was, for example, instead of saying this, if we were to put it over here, and I'll just say, just think about the reader and think about which would be more clear for the reader. So and here the reader is not me, but like a class, you should be writing towards a classmate in the class. And so sometimes it's a bit subjective, but I think in a case like this, it's actually less letters to write F than it is to write IT. So that's great. We don't lose anything for conciseness, and we can still be pretty clear. But there is this balance of like, you don't want to explain every single little detail. So there is something nice about being concise, but being complete, so the reader doesn't have to do really any thinking on their own. It should just follow really clearly to the reader what the writer is saying. Any other questions?
Yeah, if you said if the function is continuous, then it's differentiable, would that also be correct?
So I would say in that case, and here we're getting splitting kind of fine details here. Oh, sorry, I flipped this around, didn't I? No, sorry, that's right.
No, yeah, I was asking if you did continuous first and differential second, if that's okay.
Okay, yeah, I think kind of one thing that I want to point out here is, let me come back to that in a second. How about this? This is pretty close to what's above. And let me take out that. That's what I meant to say. So what do you think about this? If the function is differentiable, then the function is continuous. Anyone see a difference, maybe how someone might read a difference between these two sentences? So something like this, I don't know, if I'm reading this, I might say like, what function are you talking about? This seems to be referring to like one specific function, possibly, probably not, but a reader might infer that. Let me just say that. And so, you know, when you're writing these, you don't really want to leave anything up for inference from the reader. And I think, you know, here are some subtle things that might make a difference, right? If I change the to a, I just changed the article there. This now seems to be referring to any function, right? As opposed to like a specific thing. That's just a subtle change. I'm not saying people would lose tons of points for doing that, but I'm just trying to kind of raise some subtle things that you might want to pay attention to when you're writing these. Flipping it around, if we say f is continuous, right? This is not the same when we flip the hypothesis and the conclusion. In fact, this is a true statement over here, whereas this is a false statement over here. And if we want to prove this is false, right, we can kind of give up a pretty standard counterexample, something like that. So we do want to be careful about that, right? And again, when we're writing these conditionals, we are referring to like all such functions. Okay, any other questions? Very, very good questions. This is great. These are good things to definitely be mindful of. And so let me just say, like, sometimes the things that we're trying to prove are going to be true, and we're going to want to actually try and prove it. Sometimes the statements are going to be false, and that's something that's called disproof. And so in order to do that, in order to show that something is false, what we can do is show that its negation is true. So that's going to be something we get to eventually. So the goal here, that's why we want to practice this, is how can we negate statements? That's going to set us up for proof by contradiction eventually. So in particular, we deal with quantifiers all the time. How can we negate statements that have quantifiers? So in other words, here's a for all statement. Every student in the class is a math major. What would make this statement a lie? Like what would be the opposite truth-wise of this statement? Yeah. So these, great. So here are a couple of statements coming in. Like at least one student is not a math major. Right, and that's true. That if the original statement, every student in the class is a math major, that means what would contradict that? We just need one, right? We don't need every single student not to be a math major. So this falls in line with what some people are saying as well, with there exists a student that is not math major. That's great. So when we see something like this, it might be nice to state this using quantifiers, right? Which is what some people did there. So for example, we could say here, there exists a student in the class and I'm trying to remember from the first day of class, but pretty sure that is a true statement. Not everybody in the class is a math major. So if I want to show that this original statement is false, I just need to find someone in the class that's not a math major, right? And that would do it. And if for some reason you wanted to put some notation in there, you certainly could. Personally, I think the first sentence is clearer for somebody without the notation there. So this is the in symbol. Sorry, that was not clear. Any questions? And excuse me, if we wanted to negate statement number 2, there exists a student in the class whose first name starts with K. What would that negation look like? Any thoughts? You feel free to speak or type. The type-ins are coming in. Yeah. Yeah, so that's right. So we could certainly say like there does not exist a student in the class whose first name starts with K. That's certainly logically true. But yeah, let's start to think about how we can rephrase this as a quantified statement. That's right. And yeah, I can see that some people are saying every student in the class has the letter L as their first initial with something that came in. All students in the class have a name that does not start with K was another suggestion. So let me just say like a name, what's the opposite of a name starting with K would not be necessarily that it has to start with L, right? But just that the name doesn't start with K. So A, B, C, anything like that. Is another way that we could state this. So in other words, for all students in the class, let me just say that like, I think if we're just trying to read this, the first sentence actually probably reads the easiest. If we're like talking to each other, that's probably what we would say. The second sentence is totally correct. It just might not be the as elegant as we might state that. And so another way that you could state this again is writing this as a conditional. Then what would the hypothesis be here? You guys are chatters, typers, that's fine.
Could you say like X's name does not start with K?
Yeah. Would be another way that we could write that as a conditional. So, you know, there's different ways that we can write these proofs. We're all going to have our kind of different style, and that's fine. But one thing to point out here, and that is when we negate a for all statement, a universal quantifier, we get existential quantifier. We get a there exists sentence statement. And when we negate a there exists statement, we should get something which is equivalent to a for all statement. So if you're having trouble with these, let me just say, in general, okay, if I have a sentence like this, for all x in some set U, the statement P of x follows. So for example, for all students in the class, the statement P of x in this case would be student is a math major. Be how we might want to say this. And so if you're given something like this and you want to negate it, right? So I'm going to put that negation out in front of the entire statement, and you're stuck. You're not quite sure what to do. When we negate these universal quantifiers, what happens is one way that we can do this that's always going to work, and then I'll say that you might want to clean up the language, is we change the type of quantifier and then we negate the second part of the statement. So in other words, what that might look like in this case would be and that kind of gives us a step-by-step process to kind of start with a statement, try and negate it, and then at this point, if it's not like a very clean sentence, we could try and clean it up a little bit. So in other words, over here, we're going to make two changes. We change the for all to there exists, and then we negate P. And pretty similar if we want to negate a there exists sentence. And in this case, we can do a very similar thing. We just change the there exists to a for all. And if you're kind of not sure what I mean by P of X, it just means statement P, which depends on X, right? Student in this case. So when we're negating an existential quantified statement, we change the there exists to a for all. We negate the original P of X. And then I'll just say clean up if you can state it a little bit more clearly. Sorry, any questions about that? So this is, if you're wondering where we are in the book, this is like towards the very end of chapter 2. Okay, so maybe let's leave Raymond alone and let's take a look at 4B and think about how we could negate this quantified statement. And again, there are different ways that you might want to do it. Let me just say it might be nice initially. Right, that's what that is saying in words. And what I wrote here, I think, is like a good balance between using symbols and not overusing symbols. So like X is a real number. You know, I don't think this is making things too confusing. Using the equal sign is probably nicer than saying y cubed is equal to X. But it's nice to kind of see some words in there. So by actually writing out for all and there exists, I do think it reads a little bit better. And so if you were kind of stuck on something like this, I'm not sure where to begin. Here's a good place. Right, I can maybe just start by changing that to a for all, and then just kind of negating the result. So this is saying there exists a real number X such that there exists a real number R with y cubed not equal to X. Seems kind of awkward sentence there. Does anyone see another way that we might want to negate this? Maybe I didn't quite negate that in the best possible way. Actually did this incorrectly. If anyone's keeping score, I messed up. Yeah, that's right. Oh, sorry, no. I'm reading in those comments. Anyone see what I did wrong here? So the original statement is for all X, excuse me. What happened here?
Don't you have to replace that quantifier, the existential one, this with a for all? You
So
have to replace that one.
over here, we kind of have, here's our quantifier. And then all of this stuff over here is like the P of X. So for all X in real numbers, P of X is saying there exists. So here what we actually need to do is negate the statement P of X, okay, where P of X itself is an existential quantified statement. That's right. So if I want to negate this, that's right, we can go ahead and say something like, well, if I want to negate P, remember we change this piece over here to a for all. Something like that, right? We change the existential to a universal, and then we change the conclusion to the opposite. So we could say something here like there exists a real number So let me just read that again. There exists a real number x such that for all real numbers y, y cubed is not equal to x. Okay, so let me just summarize what we did here. So we started with right, and the idea was we wanted to negate this. So in order to negate this, we change the for all to a there exists. Okay, and then embedded in that is another existential quantified statement. Sorry, I did that too early. Right, and so that's what the negation of all of this stuff over here would look like this. Okay, again, when we negate this, we're saying, again, we're going to change that quantifier, and then we're going to change the statement P. And that's kind of where we got to there exists a real number such that for all real numbers, y cubed is not equal to x. Could someone say this in a really nice way? I don't think I've done that yet, right? I've just been kind of going through the machinery to say, okay, if I don't see how to do this right away, I know how to negate these statements. So let me just kind of do that as needed. Yeah, and so there's a nice statement that someone sent me, but not to everybody, but this is nice, which is there exists a real number x. Let me just write it down. Kind of paraphrasing what came in, but that seems like a good statement that might be more clear here. There exists a real number r such that there is no real number y with y cubed equal to x. So these can be tricky, okay? And we can have certain quantifiers embedded in other quantified statements. So I just want to say you're totally welcome to just say, I kind of understand what this sentence is saying, and I kind of understand how to negate it, and I don't need to go through all of these steps in between. Other cases, you might get kind of stumped, and it might help to go through these stages. Okay, so any other questions? This is the end of this worksheet before we start to get into doing some proofs. Any questions about these quantifiers, how we negate them? Okay, so then I want to take a look at the next worksheet, which is worksheet 4, which deals with introduction to direct proof. So this is chapter 4 of the textbook. So we're going to learn various proof techniques: direct proof, contradiction, induction, to name a few, contrapositive. Direct proof is the king of all proof. It is the most elegant way of proving things. So I'll just say it's a good place to start. It's probably the most logically clear what to do. That's why it's the nicest proof. It's going to be really clear to the reader what you're trying to do. So for your next homework assignment, you will have some proofs to write. And I just want to point out that there are some proof writing guidelines that I posted up online that you might want to take a look at, but we'll comment on some of those things, one of which is don't overuse notation. So just some terms that you might come across, I'm sure you've probably come across in textbooks, are these differences between axioms, definitions, and theorems. So an axiom is just something that is so vacuously true, we can't prove it, but it's something that we all can agree on, like something like A plus B is equal to B plus A. Try proving that. It's something that we kind of all can take for granted. Yeah, a definition is not something that you need to necessarily prove. This is just an explanation of the meaning of something. And then we have things like theorems and propositions and lemmas, and these are claims that we need to try and prove logically. Yeah, so like, yeah, here's an example of the commutative axiom for addition. An example for a definition would be an integer is even if it can be written as 2 times some other integer. So when we're proving things, okay, we can use definitions in proofs without justifying them. As long as we've talked about that definition together. Okay, for theorems, obviously we can't assume these things are true. We need to try and prove them. So when we're doing something by direct proof, this is going to apply to trying to prove a conditional statement. And the way direct proof goes is we start by assuming P is true, and then we show that if the assumption that P is true can lead us to proving that statement Q has to be true. So when you're doing things by direct proof, right, we start here, and then we want to do some logical steps in between to get and verify that statement Q is true. Okay, so a couple of other definitions. These are very, very standard. This is a good place to start proofs like even and odd numbers because we're all pretty much familiar with those ideas. So just keep in mind that when we're proving things are odd and even, we need to prove that these things occur, right? And something that you might not have heard before is this idea of parity. So we say two numbers have the same parity if they're both even or if they're both odd. Otherwise, they have opposite parity. Okay, so let's start with our first proof for the semester. Right, let's see the excitement. So we want to show we got x and y are integers. If x is even, then x times y is even. And again, we're assuming that this implies all even x's, right? Not just some of them. So if you're stuck on a proof, always a very good step is to identify what's the hypothesis, what's the conclusion. Since we're going to start with P, and then we're going to try and do some logic and eventually get the statement Q. So here, statement P is x is even. And statement Q is x times y is even. And let me just get a nice clean page to write out this proof. Okay. So so when we're kind of proving things, we should let the reader know, okay, here comes the proof. So usually we just write that by saying proof. And it's oftentimes helpful to let the reader know what proof technique you're doing. I'll just say, when you're doing direct proof, you won't have to tell me that. But if you're using another proof technique, then it's nice to tell the reader what proof technique you're doing. So just for the sake of completeness, I'm just going to leave the fact that I'm going to use direct proof to prove this. And the reason why this is helpful to me, a grader or a reader, is if you're doing direct proof, I know exactly what to look for in the first sentence, which is going to be, well, let's suppose statement P is true. And I'm going to start with this because my very next sentence is going to refer to X and Y. So it's nice to tell your reader what X and Y are referring to before I write them out in a sentence. So then your proof should start at this stage. Okay, by assuming statement P is true. And then, so let me just stop there. Any questions about that? And you don't want to assume what it is that you're trying to prove. So just be really careful about that. So sometimes to avoid that confusion, you might want to just go to what would be the last sentence of my proof. And so the very last thing that you would want to do is to show that statement Q must follow. And then in between is the hard stuff. But at least it's good to know where we're starting and where we're ending. And when you let the reader know that I'm using direct proof, I'm going to understand why things are set up that way. And I'll say one nice stylistic thing to do is when you're writing proofs, it's nice to use like the royal we, so we're in this together as opposed to like I. Okay, and then in between is logic, okay? So does anyone have a suggestion about what we could do next? And so you could either think about working your way backwards, if that's helpful, if you know, like, okay, if I wanted to show this, what would have to have occurred right before that? Or you can think about starting from the front and going forward, or at some point you can start in both directions until you meet in the middle. Does anyone have a suggestion? Let me ask you then, what does it mean that X is even?
Yeah, don't we have to define X, if X is even, then X is equal to 2A?
That's right. So since we can assume that X is even, now we can refer to the definition. Okay, and if you kind of look back at how we defined an even number, that means there exists some integer. So just so you know, right, that Z refers to integers. So logically, that's sound, right? If x is even, then logically speaking, by definition, I know that that has to be true.
And don't we have to state something similar for y, where like y is equal to b?
Yeah, so y is an integer. And what
Or should
we
we just leave that as
don't
well?
necessarily want to say something about y. We don't know what y is. And kind of the point here is, well, y can be anything. And we could think about one proof technique might be, well, there are different possibilities for y. Maybe what happens if y is odd? What would that proof look like? What would happen if y is even? What would that proof look like? And we can consider different cases for things. But I think here we can do this all in one shot without worrying about what would be true for y.
Okay, so we can leave it as 2a times y.
Sorry?
We can leave it as 2a times y is equal to x times y when we're
That's
rewriting.
right. So that's right. We want to say something about x times y. And so if it's not clear, if you got stuck about where to go from here, you can think about, well, what would have been the sentence just prior to that? Right? If we can show that, that's going to tell us that x times y is even as well. So any ideas how we can kind of connect where we stopped up here with where we need to go down here? So if I want to get an x times y on the left side, what could I do to this equation over here? Yeah, multiply by y. That's right. So I kind of want to say something about this product, and namely that it's 2 times something. So here I have an equation, right? As long as I do the same thing to both sides, the equation is going to be fine. So if you want to explain what you're doing, certainly right, if you multiply both sides by y, then we get x times y is equal to 2ay. So in other words, this does it, right? I just showed that x times y is equal to 2 times an integer. So now we've got this integer b, which is equal to 8 times y. So let me just say, sometimes when you get to the end, you know, it might not join up perfectly, and you just might want to tweak it so that things go a little bit nicer. So then we can say, okay, we've got some integer b, which is equal to 8 times y. And there's something that I took for granted here, which is how do we know that the product of 2 integers is equal to an integer? That's something that we can kind of just take as an axiom there. Okay, any questions? So I'd like us to, we've got 10 minutes. I'd like us to try and, or like you to try and one of these and see how far we can get. And then we'll pick up next class. We're going to just kind of go through a bunch of proofs next class. But I'm going to set us up into breakout rooms to try and prove 2. Where now we're going to say x is odd. I would like to show that x squared is also odd. So if you're having trouble in your groups, then kind of just start by saying what's P, what's Q, what would the first sentence be, what would the last sentence be, or however else you want to go through that one. Okay, any questions before I break this up? Okay, hi everyone. Sorry, I didn't get a chance to check in with one of the rooms. Sorry for the four of you. But let's kind of just summarize what's going on with this problem. So let's see. We've got statement P over here. We've got a statement Q over here. So just to kind of quickly run through what came up when we were talking about this. So, right, we can start by saying, let's suppose.
Oh, wait, Adam, like your screen sharing,
Yeah.
it's not showing. Yeah.
Yeah, and sorry, if anyone needs to run, I will not be offended. I am sorry for keeping you over, and this is being recorded. But I won't take too much of more of your time. Okay, now you can see that, right? Yeah, thanks. Yeah, so right, so the statement I highlighted over here, right, would be the P, and here we've got Q. So if we're going to do this by direct proof, we start with P. So we're going to suppose X is an odd integer. And we're hoping, if we're doing this by direct proof, to wind up with X squared being odd. And so similar to the previous one that we did, it might help to begin this proof by saying, well, if X is odd, what do we know about X using the definition? Right, so that tells us that X can be written as 2a plus 1 for some integer a. Okay, and so since we need to show something about X squared, might help to say, okay, well then what would X squared be? And that would equal this. You don't need to show the long details of the algebra, it's not that long, but you don't need to write out all the algebra there. That's totally fine. And then from this, we want to show that that this can be written as 2 times an integer plus 1, where in this case, B is equal to 2a squared plus 2a. And that's an integer because 2 and a are integers. And here's the most satisfying thing about proofs, is putting this little colored box at the bottom, and that means you're done with your proof. Okay, so apologies, thanks for sticking around. So for Thursday, you've got homework. In the meantime, tomorrow and on Friday, I will get your materials up for next week. So you'll have a quiz on Monday, and I'll get your next homework assignment up. So if you want to start working on that over the weekend, that will be up as well. But otherwise, I've got office hours tomorrow. Lindsay, did you have office hours this week as well?
I did, yeah. I had a few people come by this morning.
Cool. Yeah, so if you have any questions, just let us know. Otherwise, have a nice weekend, and I'll see you guys on Monday.